This will be our final lecture. And in our very final lecture, we're going to see a very interesting application of the Boursac-Ulam theorem for something in combinatorics known as Kneser's conjecture. Now, previously, last lecture, we showed how you can use the Boursac-Ulam theorem to prove the ham-sandwich theorem, which is actually an application to geometry. But in this lecture, we're going to see how you can use it to solve a problem in combinatorics. So let's discuss what Kneser's conjecture is about. And I'm going to formulate it that's a little bit different from the way it's presented in books or, for instance, on Wikipedia. So just to show you, if you were to look up what this conjecture is on Wikipedia, they would talk about something called Kneser's graph. So it's about a certain graph. And they have this nice looking graph over here. And it has something to do with what you call the chromatic number of a graph. Now, that's the way it's usually presented, but that's not the way we're going to do that. Because then we have to talk about what the graph is, then we have to talk about what a chromatic number for a graph is, and it's not exactly the most intuitive way to think about it. So I'm going to show you an alternative way that I like to think about it that you will probably find more helpful. And I like to relate it all back to the pigeonhole principle. So my students all know that I consider the pigeonhole principle to be the most important math tool. You can prove pretty much anything you want with the pigeonhole principle. So let's just say what the pigeonhole principle says. Pigeonhole principle. So what it says is, and I'm sure we all know this, but let's write this out. It says that if you have, let's say, P pigeons and H holes, and you have more pigeons than holes, then no matter how you distribute the pigeons into the holes, there will be a hole which contains at least 2 pigeons. So, for instance, let's say these boxes represent the holes. So you have 3 of them, and these dots represent pigeons. So you have 5 of them. So you randomly assign a pigeon into any one of these. So let's say this one goes here. Let's say this one goes here. Let's say this one goes there. Then because we already filled them all up, whatever the remaining ones are, they have to share a hole together with another pigeon. And this is not a class in combinatorics, but there's so many amazing things that one can prove using the pigeonhole principle. We're not going to talk about that. I imagine maybe you have seen some very elegant proofs all over mathematics which reduce the problem in a very clever way involving pigeons and holes. I'm going to show you how you can think of Kneser's conjecture as you can think as an analog of some sort of pigeonhole principle. So here's how the conjecture goes. It's going to feel very similar to this. So let us suppose you have a collection of n, let's call them items. It does not matter what they are. You can think of them as integers, but you have just a collection of n items. And your pigeons, so in the pigeonhole principle, you have a collection of objects that you're going to be assigning into holes. So your pigeons will consist of all possible subsets of size m. Okay, so you think of this n, so you think of your items as representing your universe of all items, and you're going to choose all possible subsets of size m. And in total, so as we know, so there are n choose m pigeons. Okay, so that's how many pigeons you have. And so the problem is basically this. So the question is this. What is the optimal number, let's call it h, for the number of holes, so that no matter how we distribute these pigeons into the holes, we will be certain that there is a hole that contains at least 2 pigeons. But up to this point, it feels like the pigeonhole principle. The optimal number in other words, what is this? You can say, yeah, so with the, like up to this point, this number would be one more than the number of pigeons. But here we have a different condition that contains at least two pigeons which are disjoint. So not only, so basically what we're saying is not only do the two pigeons land in the same hole, but they are also disjoint. So if that's not clear, allow me to illustrate with an example. So let's say your items are the numbers 1, 2, 3, 4, 5. Okay, so these are what we call your items. It does not matter what it is. It's just a collection of n distinct. It's just a set of n elements. Could be numbers. It could be anything. And then we're going to form all subsets of size 2. So in total, we would have 5 choose 2, which is 10, and these are going to be our pigeons. So let's write out what the pigeons are. So I'm going to write 1, 2. Now when I write 1, 2, we should understand that this is the set containing 1, 2. But I do not want to write that, so I'll just write 1, 2. Then we have 1, 3, 1, 4, 1, 5. Then we have 2, 3. By the way, if you're not going to write 2, 1, because 2, 1 is the set 2, 1, which is the same thing as the set 1, 2. So you're not going to write that. So we have 2, 3, 2, 4, 2, 5, 2, 6. I'm sorry, there's no 2, 6. We have 3, 4. Then we have, I guess, 4, 5. And I'm missing 1. So let's see, 1, 2, 1, 3, 1, 4, 1, 5. 2, 3, 2, 4, 2, 5. Oh, I forgot 3, 5. Yeah, there's a 3, 5. And then there's a 4, 5. So there's a total of 10 of them. Now, let's say we have 2 holes. Okay, so these are going to be our holes. Maybe we make it a little bit bigger. So this box represents a hole, and this box represents a hole. And you're going to distribute these 10 pigeons into these 2 holes. And let's try to do it in a way, you see, what do we want? We want the 2 pigeons to be disjoint. We want 2 things to end up in the same hole and be disjoint. And so let's try to do it in a way so they always overlap. So in this one, let's put 1, 2. Then we can put 1, 3. So notice that 1, 2, and 1, 3, they overlap. They have the number 1 in common. Then you have 1, 4, and 1, 5. So as you can see, all of these overlap. There's all overlaps. We're trying to find 2 pigeons that do not overlap. So these overlap. Now, let's say we were to pick, so let's cross out the ones that we already used. So we used 1, 2, 1, 3, 1, 4, 1, 5. So then we have to use 2, 3. Now the problem with putting 2, 3 is that if we put 2, 3 into this hole, then you can see it's disjoined from 1, 4. So we have to put it into the other hole. So let's put it into 2, 3. And then we can put 2, 4. Okay, we can put 2, 4. And what else can we put? We can put, so 2, 4. We can put 2, 5. Okay, we can also put 2, 5, like this. And we have 3 more things to put. So we have to put a 3, 5. Now, you either put a 3, 5 here or here. If you put a 3, 5 in this one, in the first one, we're going to have a problem because then 3, 5 is disjoint from 1, 2. If we put a 3, 5 in here, then we have a problem because then 3, 5 and 2, 4 are disjoint. So you can see that if you have 2 holes, that no matter how hard you try to distribute those pigeons into those holes so that they are non-overlapping, it's impossible to do that. So if you have 2 holes, then you're guaranteed for 2 pigeons to overlap in the same hole. Now, what if you had an extra hole? Well, if you have an extra hole, you have a little bit more freedom, right? You have a little bit more freedom. So let's, and then what you can do is you can put 3, 4 in here, 3, 5, and you can put 4, 5. And now you can see that these 2 overlap, these 2 overlap, and those 2 overlap. So we have found the way, okay, so we found the way to distribute So let's basically say what this is. So we found a way to distribute these pigeons among 3 holes so that any 2 holes have overlapping pigeons in them. I keep on saying pigeons because I hope that makes it easier to understand. If I keep calling them sets, that might be confusing because you might perhaps get confused and think about this set. So that's sort of like the universe from where the items are chosen, but the pigeons are all subsets of size 2. So that's why I find it helpful to just keep on referring them for pigeons and holes. So it's sort of easier to keep track of what we're trying to say. So there's a way to distribute them with 3, but there is no way to distribute them in such a way with 2 holes. So the optimal number is 2. That's the optimal number. That's as big as you can go. Obviously, the more holes you have, the more freedom you have. And if you have too many holes, then you can, of course, if you had like 1,000,000 holes, then you can just put them, you can put 1 pigeon into each hole separately, and then they will never overlap. And then you cannot even find 2 that, I mean, so it's not that you're going to find 2 that overlap. You're not even going to be able to find 2 that are in the same hole. So the real interesting question here is how high can you go? So I'm going to tell you the solution to this problem. So let's reformulate the problem. So here's the problem. This is called Kneser's conjecture. So let me say this again. The actual conjecture is formulated in terms of graph theory and chromatic numbers. That's not the way we're doing it because I think that's a bit more confusing. And especially if you're not familiar with graphs and chromatic numbers, then you're not going to be comfortable using that kind of terminology. So this is why I find it a lot more intuitive and a lot easier to think in pigeons and holes. So this is Kneser's conjecture. It says that let n be the number of items and consider all n choose m subsets of those items. So you're going to think of these as your pigeons. So your pigeons are all possible subsets of size m. And the question is, what is the largest number of holes h, so that if those pigeons are distributed among those holes, then we are certain. So it's all about being certain. It's not, we're not saying that, like, we're saying that you can always conclude this no matter what you do. We're not saying that there is a way so that they overlap. We're saying that no matter what you do, no matter how you choose to distribute them, it will always work. Like, maybe to make it just a little bit easier, like if we just go to the classical pigeonhole principle, if you have 3 items and you have 2 boxes, 2 holes, no matter how you try to distribute these 3 pigeons into these 2 boxes, both of them end up in the same box. Now, if you have 2 pigeons in 2 boxes, you can put 1 pigeon into each box, and then you're no longer certain that 2 of them are in the same box. Now, it could happen that 2 are in the same box, but you're not certain of that. It could or could not. So it's all about being absolutely certain that this property must hold. Then we are certain that there is a hole containing 2 pigeons. And when we say 2 pigeons, of course, we mean at least 2. There could be other ones, but at least 2 pigeons which are disjoint. They're disjoint assets. And we assume, and this is for silly reasons, which I will explain soon, that 2m has to be less than or equal to n. Because otherwise it's impossible. Like, let's say you have 5 items. So here n is equal to 5. And you're going to choose a subset of size 3. Well, if you're choosing a subset of size 3, then any 2 subsets of size 3 will automatically overlap, because you have a total of 6 elements, but you can only choose from 5. So they will always overlap no matter what. So then it would be impossible to do that. So that's why I mean for silly reasons. So we have to assume that 2m never exceeds n. And Kneser's conjecture says that this number h, this optimal number, is equal to n minus 2m plus 1. That's Kneser's conjecture. That's the optimal number of holes. That's as big as you can go. If you go one higher, then there is a way to distribute it with so that all of them overlap. So this was a problem that was formulated, according to Wikipedia, in around 1950s, and it remained an unsolved problem in combinatorics. And if you're confused and you're like, well, it feels like an easy problem. Well, if you've not had much experience with combinatorics, combinatorics is a little bit like number theory in many ways, that there's lots of problems in combinatorics that they seem very simple, but they're very hard to prove, because you have to understand that, like, you have to come up with some kind of general argument. If you try to brute force yourself in some kind of proof where you say something like, well, let's say box number 1 has only 1 element and box number 2 has 2, and then you start considering all different subcases that you can have. There's just too many subcases to consider, and then the solution becomes more and more complex the larger the numbers get. The number of possibilities to consider grows exponentially and all of that. So you need some kind of general argument that no matter how you distribute, that you can always be certain that that you can always find 2 that are disjoint. So you certainly need some kind of general type of an argument. And it was solved in the 1970s by, I am not sure how to pronounce his name, so Laszlo Lovász, I'm not sure. But so just to show you, let me just bring this up. So here's the mathematician who solved it. He was actually recently awarded, as you can see, he was awarded the Abel Prize very recently. And he's known for many things, but most of the mathematics that he has contributed is in combinatorics, discrete mathematics, graph theory, things like that. That's what most of his work is. He also done some work in computer science, and that's what the Abel Prize was awarded to. It was like lifetime contribution to those areas of mathematics. He was not given the Abel Prize for solving Kneser's conjecture, but that's just one of many, many accomplishments that he has. And the interesting thing about his solution is he cleverly used topology to solve this. So that's the part which is quite amazing. And nowadays people call this topological combinatorics, which what it means is you're solving problems in combinatorics by using techniques from topology. So that was like the first instance in mathematics where people borrowed tools from topology to help you solve a problem in combinatorics. And that's what we're going to discuss. Now, before we do anything, I just want to go back to the example that we just did. In the example that we did, we had 5 items, and the pigeons were of size 2. So then the optimal number would be 5 minus 2 times 2 plus 1. So that would be 2. So we saw that if you have 2 holes, then you're guaranteed to find 2 pigeons in the same hole that are non-overlapping. But if you have 3, then there is a way to do it so they do not overlap. Right? There is a way to do it. There's also a way to do it so they do not overlap, but we want to. That's not really what the problem is about. The problem is about being certain that you can that no matter how you do it, they will not overlap. So Uh, so basically what you have to show is you have to show this is the optimal number. So you have to show that if this is the number of holes you have, then you can always find two pigeons in the same hole that do not overlap. And then the other part is to show that if you go one more, that if you have n minus 2m plus 2, if you go one more, then there is a way to do it so that they do not, so that they always overlap no matter what. So that's actually the easy one. So I want to discuss this first. I want to show you that you cannot, if you go one higher than this number, then there is a way to do it in the way so that the pigeons always overlap. So that's something that people kind of knew from the very beginning. That's not too hard to do. And I think it's just easiest to just illustrate it in an example. So let's say we have 20 items. So in this example that we're going to do, we're going to use concrete numbers. But the nice thing about the argument that we're about to show is that it will very easily generalize to any arbitrary collection. I just find it a little bit easier when you think about what happens in a very concrete setting with numbers. And once you understand that and you see that it's not too hard, it's not difficult to then convert that into like a more formal proof for any general case. And let's say we have m is equal to 5. So this means that all pigeons are sets of size 5. Or maybe you can say subsets, because the subsets are coming from a collection of 20 items. Maybe to make it easier, you can even call the items 1, 2, 3, 4, up to 20 to make it easier. So then H, according to Kneser's conjecture, the optimal number would be n minus 2m plus 1. So in this case, it would be 20 minus 10 plus 1. So that would be 11. So if you have 11 holes, then you're guaranteed to find two pigeons in the same hole that do not overlap. But let's say we have 12. So let us construct a way to distribute these pigeons into 12 holes. So we're going one more than that, into 12 holes, so that in each hole the pigeons overlap. So let's see how we would do that. So here's how we approach this. So this is what we're going to do. We're going to call this hole 1, hole 2, and let's go up to hole 11. I'm specifically going to stop at 11. We're going to have 12 holes, and then we have one special hole, which we're going to call H12. So here's what we do. So if P is a pigeon, so again, what is a pigeon? A pigeon is simply a subset of size 5, right? It's just you're choosing 5 of these, so that's what a pigeon represents. So then, if you look at the minimum number that's located in P, this could be 1, it could be 2, and at the very most, it could be the number 15. The reason for this is because the largest possible collection, the largest possible way of choosing 5 of these would be 20, 19, 18, 17, and 16. 1, 2, 3, 4, 5. Okay. Oh, so the minimum, so sorry about that. So that would be the minimum. Okay, so if you pick, so if P is a pigeon, then the minimum number that's located in P will range from 1 to 16. Okay, so if the minimum of P is a number between 1 to 11, then put P into that hole. Okay, so we have, these are the 11 holes. So you calculate the minimum for P. Now, then you would just put P into that hole that you have. Okay, so So then you would just put them in here. And then it's clear that if you have two pigeons that end up in the same hole, so let's say you have P, so let's say P ends up in H2 and P prime ends up in H2, then these two must overlap because the minimum number for P is 2 and the minimum number for P prime is 2. So then P and P prime have 2 in common. So then they overlap. So if any of the pigeons end up in any of these holes, they automatically overlap by construction because the whole number is an item that's part of the pigeon, right? It's an element in the pigeon. But what about the other ones? So the remaining, so the big pigeons are placed into H12. That's the last remaining hole. So what's a big pigeon? So a big pigeon is when the minimum number, so what does it mean to be a big pigeon? So you look at the minimum number. So if the minimum number of the pigeon is 12, 13, 14, 15, or 16. That's what we mean by a big pigeon. So then those pigeons are then placed into this remaining hole. Okay, and then we claim, now, we claim that if P and P prime are in hole number 12, then P and P prime must overlap. Okay? So the reason for this, so why? Because P and P prime, they have to be chosen, they have to be subsets of these numbers, 16, 17, 18, 19, 20, right? Because the minimum number in the big pigeons is at the very least 12. So whatever you're choosing, the minimum number is at 12. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, right? There's 9 choices. But P and P prime each contain 5 of those. So P and P prime must overlap. Okay, so you've just produced a pretty nice, convincing argument that it's possible to distribute those pigeons in a way so they always overlap in every single hole. And I mean, it basically just came down to this, that with the big pigeons, you're choosing, the items that you're choosing are from 12 and onwards, and if you just enumerate them, there's only 9 such things you can choose from, and P prime by assumption are pigeons of size 5. So they must overlap, because otherwise, I mean, otherwise they will exhaust, right? There's 5 and 5, that's 10. Otherwise they will exhaust all of those. So they must overlap. And the nice thing about this argument is that there's nothing special about the number 20 or 5. You can really do this as a more general type of argument and turn it into a more general proof. I just think it would have been more confusing if I just did this in terms of n and m. Then it's easy to sort of lose track. But you can play around with this and turn it into a more formal proof if you want to. So this shows that if you go, if h is this number, and if you go one more, then there is a way to distribute the pigeons so they always overlap. And the more difficult thing is to prove that it's impossible to do that when h is this number, which is not, I mean, that kind of makes sense. Like anytime you claim that something is possible, you just have to produce an example that does it for you. But when you say something is impossible, you're essentially proving a theorem. You're sort of showing that no matter what configuration you can possibly imagine, some kind of property must always be satisfied. Just think back to topology. It's often easier, though not always, but it's often easier to show that two topological spaces are homeomorphic. You just have to produce a homeomorphism function. But when you're showing that two topological spaces are not homeomorphic, that is generally a lot harder because you have to give some kind of argument why it is impossible to produce a homeomorphism function. And there's an infinite number of functions to consider, so you cannot just try every single one of them out. Now, so here's the part which is interesting. So in order to prove the to solve Kneser's conjecture using topology, we need a variant of the Boursac-Ulam theorem, which is known as the I'm not even sure how to pronounce it. I'm going to maybe show you an interesting book. So let me show you this interesting book. So there's an entire book written on the Boursac-Ulam theorem. Now, this is a book not really so much on topology. It's, as the title says, it's on combinatorics and geometry. And you're using the Boursac-Ulam theorem to solve many problems for you. Now, this book is kind of recent. It's not that long ago. And the author of this book, I decided to look some information about this author, and then unfortunately I found out he died not that long ago. So he was fairly young. It was like 50 years old. So, but this book is not that old. It's fairly recent. And it shows all different ways, interesting ways the theorem can be used. So he talks about the ham sandwich theorem, something about necklaces and partitioning necklaces, and then he talks about Kneser's conjecture. So this is where I'm going to take the proof from, though I present it a little bit differently without using chromatic numbers. So this is so as you can see, it's something about the chromatic number, but that's basically what we're doing. And we're going to use a theorem which in this book, he calls this theorem, so let's see. I wonder if he even gives a name to it. Okay, so here's the theorem that we're going to use. So this is one of the versions of Boursac-Ulam. So he calls this the Lusternik-Schneiderman theorem. Okay, so I had to look that up because I'm not even sure how to pronounce their names. But this is like one of the variants of the theorem. So I'm going to go through this proof. This is actually a very nice proof, very elegant proof. So this is a variant of Boursac-Ulam. So Boursac-Ulam comes with many variants. So let's show known as the, let me just refer to it as the LS theorem, because I'm not sure how to spell their names or pronounce it. So Lusternik-Schneiderman or something like that. So here's what it says. It says that if Sn, so this is the n-dimensional sphere, is covered by, let's say, closed sets. Let's call these closed sets C1, C2, Cn, and we need one more, Cn plus 1. So what does it mean to be covered? It just means that Sn is a union of these closed subsets. Okay, so you expressed the n-dimensional sphere as a union of closed subsets. So then there exists a point P on Sn and a closed set Ci such that P and its antipodal point negative P both belong to Ci. They both belong to Ci. So to put it very simply, what we're saying is if we express Sn, the n-dimensional sphere, as a union of closed subsets, right? Closed sets Those closed sets could be overlapping. That's fine. We do not really care about that. But if it's as a union of closed subsets, and this is n plus 1 closed subsets, then we can find an antipodal point. Then we can find a pair of antipodal points which are contained in the same closed set. That's what it's saying. So it feels very similar to Borsuk-Ulam. And in fact, you can prove this using Borsuk-Ulam. So let's give a proof of this. Okay, it's actually a very short proof. And if you're interested, you can look in the book that I showed you using the Borsuk-Ulam theorem, and it shows all different variants in that book, which are used throughout the book. But this is the Borsuk-Ulam theorem that we discussed. This is Borsuk-Ulam theorem. So it says that if f is a continuous map from Sn to Rn, is a continuous map, then there is a point on Sn so that f of p is equal to f of minus p. And we're going to use this to prove this variant of Borsuk-Ulam. So here's how the proof goes. So let's write proof. So maybe we're going to suppose that each p, we're going to suppose that for each p, we're going to suppose that if a point belongs to Ci, the negative p does not belong to Ci for all p. So for all points on the unit sphere. So we're doing it by contradiction. So the LS theorem says that you can find a pair of antipodal points that belongs to some closed set Ci. And we're assuming that no matter what point you pick on the n-dimensional sphere, if a point belongs to Ci, then its antipodal point does not belong to Ci. And we're going to get a contradiction out of this. So we're going to define the functions f1, f2, fn plus 1. And actually, if you look at the proof that we're about to give, it will feel very similar to the same kind of technique that we used when we proved the ham sandwich theorem. So we're going to define functions. We're going to define a total of n plus 1 functions. And these are going to be functions from the n-dimensional sphere into R. These are going to be real valued functions. They're going to be continuous by fi. So every one of these functions is going to be defined as follows. This is just going to be the distance between x and Ci. So what's the distance? So if you're confused what we mean by the distance, like what do we mean by the distance? It just means this. So the distance between x and Ci. So x, so maybe I'll draw a picture right over here. So this is your sphere Sn, and then somewhere on the sphere you have a closed set. You have like a closed set. And now if you have a point x on the sphere, how do you find the distance from x to whatever that is? So the way you do it is, this is sort of the reasonable way, is you're going to take the distance between y minus x, where y is an arbitrary point in that closed set, and you're going to consider the infimum as you range y over all of these. Okay, so this is actually the reason why we want these to be closed sets, because if these are closed sets, they are compact sets. They're compact subsets of Sn. Sn is compact. And now recall some basic point set topology, that if something is compact, the closed subsets are also compact. So these are compact subsets, and because they're compact subsets, the minimum is achieved. That's sort of what we call like the extreme value theorem. If you define a continuous function on a compact set, real valued function, a minimum is achieved. So the distance, the minimum will be achieved. And furthermore, if the point is outside this closed set, then the distance must necessarily be positive. And it will only be equal to 0 if the point is in the set. So that's kind of like the reasonable way to do it, and this is why you want them to be closed. So that's the way you define the distance function. And now you're going to construct the function f from from Sn into Rn by the rule that f of x, and this is something we saw with like the ham sandwich theorem, is you're going to take every one of these functions that you've constructed and you're going to subtract some fixed function away from it. Let's say the last function on our list. Fn of x minus Fn plus 1 of x, like this. So this is what we do. And now we are in position. So notice it's Rn because we're subtracting the last function away from the other function. So we have one fewer component. And now by the Borsak-Ulam theorem, we can find P and negative P antipodal points so that f of P is equal to f of negative P. So what does this mean? So thus f I of P minus Fn plus 1 of P is equal to, so I'm just equating them. So if you put P into f of P, that would mean f1 of P f minus Fn plus 1 of P, then f2 of P minus Fn plus 1 of P, and so on. So as I ranges from 1 to n, you have, these are the components. So these components have to be equal to those components, so that these are equal. Minus Fn plus 1 of minus P. And you can do the same thing with the other one. Let's say you have Fj of P minus. So if you choose the different index, right, to have an index I, you choose a different index j, you have the same relationship. So now if you subtract them, so we get fi of P minus fj of P is equal to fi of minus P minus fj of minus P. And this is for all I and j. For all I and j between 1 and n plus 1. Okay, so let me just explain what we just did. So f of P is equal to f minus of P. So this means that if you choose the ith component on this side, which is this, and you choose the ith component on the right side, which is this, they have to be equal. And likewise, if you choose the jth component here and the jth component there, you have this relationship. And now if you subtract these two equations, and you subtract these two equations, you have that fi of P minus fj of P is equal to this. And this is for all I and j between 1 and n plus 1. If it bothers you, you might say, well, what if j is n plus 1? Well, if j is n plus 1, then you already have that relationship. Fi, this is I, this is j, I, and that's j. So you have this relationship that for all I and j, this kind of relationship must be satisfied. So here's how we get our contradiction. So we know that P is a point on Sn, and Sn is a union of these closed sets. So P belongs to Ci for some I. And likewise, minus P is on Sn. So minus P belongs to Cj for some j. And furthermore, the two indices, I and j, must be different. The reason for this is because that's what we're assuming. We're assuming that each of these closed sets never contain antipodal points. So if P belongs to Ci, it does not belong, so negative P does not belong to Ci. So they must come from two different closed sets. And now notice where the problem occurs. So this is going to be quite interesting. So let's look. So So this is the part which is interesting. So if you do fi of p minus fj of p, because fi of p is on ci, the distance, so remember how this is defined. This is the distance between the point and the ith closed set. So because it's on ci, the distance is 0. Whereas whatever this is not, this point P is not in Cj. So, so here the distance has to be positive. So here the distance is positive. I'm thinking that it is conceivable maybe that the point also belongs to Cj. Oh, no, that cannot happen, right? The point P cannot belong to Cj, because if it belongs to Cj, then minus P is in Cj, and that violates our assumption that all of these closed sets never contain their antipodal points. So this is not in Cj, so this has to be positive. So whatever this is, it's 0 minus a positive number. And this, so whatever this is a negative number, right? This is a negative number. But it's equal to, we said, this is fi minus p minus fj minus p, right? This is what we've said up here. So then, but then this is equal to 0 because minus p is in Cj, and then this is positive because minus p is not in Ci. P is in Ci, so minus p is not in Ci, so this is positive. So then this difference is a positive number, a positive real number. And this is the contradiction, that a negative number is equal to a positive number. So that's the contradiction, and so that cannot happen. So that's the proof. So it's a nice proof. It's not too bad. And actually, what's interesting is, even though we proved it for closed sets, you can replace closed sets by open sets. It's also true for open sets. You have to use a different argument, open sets. And if you're interested, you can look in that book to see it discussed for open sets. And in fact, you have more, it could be more general. You can allow these sets, you can allow some of these to be open and some of them to be closed. So that's also okay. So this is the result that we need. And now we're going to use this to prove Kneser's conjecture. So here's how it goes. So this is going to be the setup. We have n items, and 2m will be less than or equal to n. Otherwise, there is no Kneser's conjecture. It's somewhat silly, as we remarked before. And consider all pigeons P, where P is a collection, or you can say is a set of, is a subset of size m. Okay, and we're also going to assume each pigeon P has been assigned into a hole in such a way so that if, let's say, P and P prime are two pigeons in hole I, in some hole, in the same hole, then P and P prime overlap. So we're going to get a contradiction out of this. So also assume that we have H holes where the number H is equal to n minus 2m plus 1. Yeah, where h is this. So that's what we're trying to prove. We're trying to prove that this number h is the optimal number, and that if you distribute the pigeons among the holes, then they must overlap. I'm sorry, you must necessarily find two of them in the same hole that are disjoint. So we're doing this by contradiction. We're going to assume that all of these pigeons overlap whenever they come from the same hole. So here's how we're going to set this up, and this is very clever. The proof is not too long, but it's very clever. It's not something that one would typically think of. So we can assume that the n items are points on the sphere SH. So in all of the examples that we have considered, when we written out our items, it was convenient to label our items 1, 2, 3 up to the number n. But it does not really matter what those items are. So let's just assume, here's going to be convenient to assume that those items are just n items that have been placed somehow on the sphere. And furthermore, these n items are placed on this sphere, this h-dimensional sphere, in what is known as general position. General position is a common phrase in geometry. Not sure if you've seen it before, but basically what it means is if you were to take a bunch of points and put them down randomly, there's not supposed to be any kind of coincidences. So if you're confused by that, let me illustrate. If you randomly put 3 points in the plane, you will create a triangle. It is possible to put 3 points in the plane in such a way that they're part of the same line. We call that a coincidence. That's not supposed to happen. Randomly, they will not be part of the same line. In the exact same way, if you have 4 points in R3, will generally, that's what we mean by general position, generally not be part of a plane. If 4 points could be part of the plane, that's possible, but that's not what happens in general. That's called a coincidence. That's not supposed to happen. That's why we call it a coincidence. So, called general position. Now, you might be asking, what exactly does it mean to be in general position in the context of this proof that we're about to write? So I find it helpful to not tell you what it is at the moment, and when we reach the end of the proof, you're going to notice a certain coincidence that arises. So let's just, for the moment, leave this a little bit vague, but we will clarify at the end of the proof. I think that would be an easier way to follow the proof. So here's what we do next. So we have H holes for each point X on this H-dimensional sphere. We define, let's call it capital H of X. This capital H has nothing to do with this lower h. H is the hole, capital H is the hemisphere. We define H of X, this is the open hemisphere. In the direction of X. So to draw a picture for you, if we have our sphere, so this is our sphere SH, and you pick a point on, and you pick a point X on the sphere, that's a point on the sphere, the hemisphere, so the way you get the hemisphere is you would just draw that vector, and it'd just be the perpendicular, right? So you get this, right? Something like this, right? You get this. You call that H of X. That's the hemisphere. So that's like the picture of how it looks like. It's the open hemisphere, so it does not include the boundary, the equator. If you want to write this out more formally, you would just say more formally, h of x would then be points on this sphere with the property that the dot product between x and y stays positive. Because the dot product will tell you the angle relationship between the two vectors. So if you have something that is part of the hemisphere, then the angle between x and any point on the hemisphere, the angle between those two vectors is acute. And since it is acute, the dot product is positive. If it's on the equator, the dot product is 0 because it's perpendicular. And if it's facing on the opposite side, then the dot product will be negative because it's an obtuse angle. So you can talk about angles by using the dot product. So that's how you can formally define this hemisphere. But I find it easier just to think of this picture. So for every point on the sphere, you can construct the open hemisphere that's pointing in that direction. And now, for each I, 1, 2, up to h, so h is how many holes we have. That's also the dimension of the sphere. We construct the following open sets. So these are going to be open subsets of the sphere. So ui, this will be, so these will be points, say points x on sh, so that the hemisphere, maybe I'll write it, yeah, so that the hemisphere drawn at x contains a pigeon from hole I. So let me draw a picture to hopefully clarify what we're doing. So this is our sphere, and on the sphere, here's what we did. So this is what we did. We took the n items and we placed them in general position on the sphere. So we have maybe an item over here, an item over there. So we have items, we position our items all across the sphere or something like this. And then if you pick a point x, let's say that's x, you're going to draw the hyperplane, you can say, that cuts through it. So you get your hemisphere. And then you see, when you get your hemisphere, some of the items, right, the points in blue, those are the items, are part of that hemisphere. And some of them might not be. So you have some of the items being part of the hemisphere. Now, if you can find, so what is a pigeon? A pigeon is a collection of m items, right? We're considering all subsets of size m. So a pigeon is a collection of m items. So if you can find m items, right, so m of those blue points, that all come from the same hole, right? Every pigeon is going into some hole. So if you can find a pigeon that is coming from hole I, then that's how you construct this set ui. So ui are all of the points, so that if you draw the hemisphere at that point, the hemisphere will contain a pigeon coming from hole I. So that's the way this is done. The reason why these are open sets, it just has to do with the set that you have a finite collection of items. So if you found a hemisphere that contains a bunch of items, you can slightly, like infinitesimally slightly move that plane a little bit back and forth without making any of those points escape out of that hemisphere, right? It's an open hemisphere. So if you have an open hemisphere and it contains a finite set of points, if you slightly perturb it, just slightly move it, it will still continue to contain those points. They're not going to escape. So that's why this is an open set, because if you have x and you slightly move it around, you slightly perturb it, anything in the neighborhood of x will also contain the same pigeon. So this is why this is an open set, because it contains all of the points locally around it. Okay, so that's what we have. So we constructed. So we have constructed these open sets, U1, U2, up to UH, and these are open subsets of SH. And now we're going to construct the last remaining set. So this is just whatever is left over. So it's SH, take away whatever we've used up. So this is just the last remaining possibility that we can have. Okay, so this is of closed because it's a complement of open sets. Then we can apply the Lister-Nick-Schneiderman, or whatever you call it, theorem to this collection, U1, U2, UH, and C. Remember how the theorem goes. When we stated the theorem, we said that the number of closed sets has to be one more than the dimension of the sphere. And that's exactly what's happening. Our sphere has dimension H. So we have H open sets and one closed set. And we remarked that even though we proved this theorem for a closed collection, it works just as fine for an open collection and also for a mixed collection where some of the sets are open and some of them are closed. That's fine. If you're bothered by that, you can, of course, resort back to that book as a reference to see how they explain it. And now we're going to see something interesting. So thus, we can find an antipodal point, P in SH, so that, let's say, P and minus P belongs to the same set. Right? It belongs to one of these. So let's consider what happens. So there's two cases. So case one, P and minus P belong to UI. So then the hyperplane, I'm sorry, not the hyperplane, the hemisphere at P contains a pigeon, let's call it capital P, from hole I. And H minus P. So this is the definition of UI. UI is the collection of all points on the sphere so that the hemisphere at that point will contain a pigeon from hole I, right? That's the way we defined it. So if negative P is in UI, then that means the hemisphere at minus P, at the antipodal point, contains a pigeon, call it P prime, from hole I also, right? Because they're both coming from the same open set UI. But here's the problem. But then P intersect P prime is empty. It's an empty intersection. The reason for this is because these two hemispheres, right, since the hemisphere at P and the hemisphere at minus P is empty, right? Like, I mean, I think the picture makes this very clear that if you were to draw a hemisphere this way and a hemisphere that way, they clearly have nothing in common because they're antipodal points. You're just cutting the sphere into two disjoint hemispheres. This is why it's important that they're antipodal points. So whatever pigeon you can find in this one and whatever pigeon you can find in that one, you've just found two pigeons. They both come from the same hole, and both of those pigeons is empty. And why is this a problem? This contradicts our assumption. This contradicts our assumption. So what was the assumption? So the assumption was, so this was the assumption we made in the very beginning. So this was the setup. We're going to consider pigeons, and we're going to assume that every pigeon has been assigned to a hole in such a way so that if two pigeons come from the same hole, then they overlap. In other words, we were supposing Kneser's conjecture was false, and that would be the implication. That would mean that there's a way to assign those pigeons so that they always overlap. Okay, so this is impossible. So what's case two? So what's case two? So case two is then P and minus P belong to the other remaining set that we did not use it. The other possibility is the antipodal points belong to C. Belong to C. And you have to recall what C was. Recall that C was just the leftover points. So that was your sphere, take away U1, UN. So those were the leftover points. So what does this mean? So then the hemisphere at P contains at most m minus 1 items. So the picture here is if you position your items on the sphere and you draw your hemisphere, then your hemisphere, so the items are, so the original items that have been placed on the sphere, so the plane can only contain m minus 1 items. The reason for this is because if this hemisphere contained m items, then that's a collection, that's a subset of size m. And the subset of size m is a pigeon. And that pigeon is going into some hole, right? Some hole from 1 to h. So whatever, if it had m items, that would give you a pigeon. And that pigeon has been assigned to some hole. So from what, so u1 to uh, it would therefore have to be among, right? It would have to be among, whatever that point be, will have to be among those. But we're assuming we're picking something that's not among those. So that means whatever items are present in this hemisphere, you cannot have m of them. So you have at most m minus 1. Okay? And in a similar way, h minus p, that's the other side, contains at most m minus 1 items. So thus, the equator, so what's the equator? The equator would then be SH, take away HP union H minus P. That would be the equator. So keep in mind that these are open hemispheres. So that's one side of it, that's the other side of it. So the last remaining piece is the equator. So let's call the equator, that's the equator. So let's call this E for equator. So then the equator will contain at least, so how many points we have in total? We have in total n items. We have n items. And then from n items, we're subtracting m minus 1, right? We're subtracting the items that could occur on this hemisphere, and we're subtracting m minus 1 items that could occur on the other hemisphere. So this becomes n minus 2m, and this is plus 2. Now, if you see what that is h plus 1. Why is that h plus 1? That's h plus 1. Let's just go back all the way up again. Let's just go all the way back up. See, that's the optimal number in Kneser's conjecture, n minus 2m plus 1. So we're getting one more. We're getting n minus 2m plus 2. We're getting one more. So the equator will contain at least n minus m minus 1 minus m minus 1. So do a little bit of manipulation, n minus 2m plus 2. So that's h plus 1 items. Okay, but here's the problem. But then these items on the equator are not in what is known general position, since we can find a hyperplane. I mean, here we're working in higher dimensions, so we call it a hyperplane. A hyperplane is it's a subspace. It's a subspace of dimension 1 less. So we can find a hyperplane passing through the equator, E, that contains these items. So that then ends up violating what we said. So we've said that if you have 3 points in the plane, in general, you're not going to find the line that passes through 3 points, right? A line is dimension 2, and you have 1 extra point. A plane, a regular plane, has dimension 2, and it can contain 3 points, but in general, it will not contain 4 points, right? It's always about 1 more. So we have a sphere of dimension h, but we have h plus 1 items on the equator, and you can pass a hyperplane through the equator, and then that would violate the fact that the points have been chosen in general position. And that right there is a very elegant proof of Kneser's, a very elegant solution to Kneser's conjecture.